All right, let's jump right in. Take a look at this polynomial. How in the world would you find its roots? I mean, you could guess and check, right? But there are literally infinite numbers to try. So what if I told you there's a tool, a mathematical secret weapon, that can take that endless search and shrink it down to a super short, manageable checklist? Well, today, we're cracking open that exact tool, the Rational Root Theorem. I really want you to think of this thing as your official detective's guide for solving these polynomial mysteries.
Now, you probably already know that if you can find some number c that makes the whole function equal 0, then bingo, you found a factor. But that's the whole problem, isn't it? With a bottomless ocean of numbers to pick from, finding that one special c feels like searching for a needle in, well, a universe-sized haystack.
And this is where our hero, the Rational Root Theorem, steps onto the scene. You can think of it as the ultimate detective's checklist. Its whole purpose, its reason for being, is to take that impossible, infinite search and slash it down to a short, finite list of suspects.
So, what does this theorem actually say? It's surprisingly simple, but it is incredibly powerful. It says that for any polynomial with nice, clean integer coefficients, any rational root, and that just means any root you can write as a fraction, has to be in this very specific form, p divided by q. Okay, so what on earth are p and q? Let's break it down, starting with p. P is just any factor of the constant term. You know, that plain old number hanging out at the very end of the polynomial, the one with no x attached to it?
And q, well, that's its partner in crime. Q is any factor of the leading coefficient. That's the number way out front, attached to the x with the highest power. So just remember, P comes from the back, Q comes from the front. That's the key.
All right, enough theory. Theory is great, but now it's time for the fun part. Let's actually start cracking a case and put this theorem to work.
Hey, does this look familiar? Yep, we're circling right back to the problem from the very beginning. Only this time, we have our secret weapon. Let's see how it does.
Okay, time to build our list of suspects. First up, our p-values. They're the factors of our constant, -6. So that's plus or minus 1, 2, 3, and 6. Easy enough. Next, q. Those are the factors of our leading coefficient, which is just 1. So q is simply plus or minus 1. Now we form all the possible p over q fractions. And look at that. We just went from infinite possibilities down to just 8 suspects. Now we have to interrogate our suspects. Let's start with an easy one. X equals 1. We'll use synthetic division, which is a super fast way to test for roots. And look at the result. See that 0 in the bottom right corner? That, my friends, is the smoking gun. Getting a remainder of 0 means we've hit the jackpot. We've just confirmed that x equals 1 is a root. And here's the best part. The bonus prize for using synthetic division is that the other numbers on the bottom row give us what's left over. In this case, a much friendlier quadratic equation that we can easily solve. And that quadratic, x squared minus 5x plus 6, factors beautifully into x minus 2 times x minus 3. So there we have it. We've completely factored our original cubic polynomial. The final zeros are 1, 2, and 3, case closed. Okay, that was a pretty good warm-up. But what happens when that leading coefficient isn't a nice, simple 1? Let's take on a tougher case. So this time, our p-values come from the factors of -3, and our q-values come from the factors of 2. Now, when we make our p over q list, we get some fractions in the mix. Our suspect list is a little longer, sure, but it's still totally manageable. Let's try testing x equals 1 again, just to see. We run it through synthetic division and, we get a remainder of -12. Now, this isn't a mistake. It just means x equals 1 is not a root. So we cross it off our list and we move on to the next suspect. You know, a little trial and error is just part of the detective work. So let's try x equals 3. We run the numbers and there it is, a remainder of 0. We found our first root for this one. The leftover part, 2x squared plus 3x plus 1, also factors pretty easily. And here's our final result. The zeros are 3, -1/2, and -1. See? Even when you've got fractions involved, the process is exactly the same. But what happens if you test every single candidate on your list and none of them work? Does that mean you messed up somewhere? Well, not necessarily. Let's take a look at what it means when the trail goes cold. Check out this polynomial. Our p and q values both come from the factors of 1, so our only possible rational roots are just positive or -1. But when we test them, f of 1 is 3 and f of -1 is -1. They both fail.
So what does this mean? It doesn't mean the theorem failed us. Actually, it did its job perfectly. It told us that if there were any rational roots, they had to be 1 or -1. Since neither one worked, we can now say with 100% certainty that this polynomial has no rational roots. The roots might be irrational, or maybe even imaginary, but they are definitely not simple fractions. The theorem's job is done.
Okay, to wrap things up, let's go over a couple of pro tips to help you avoid common mistakes. And then we'll get to the real payoff, where this abstract math stuff actually shows up in the real world. Let's talk about 2 common traps people fall into. First, whatever you do, don't forget the plus or minus signs. You'll literally cut your list of suspects in half if you only test the positive ones. And second, remember that your list is a list of candidates. They're not confirmed roots. You're the detective, you still have to do the work and test each one. So, why should you care about any of this outside of a math test? Well, how about computer graphics? Anytime a video game engine renders reflection on, say, a car's curved windshield, it's actually solving a polynomial to figure out where a ray of light hits that surface. And the rational root theorem is like the engine's first pass, a super fast way to find all the nice, easy intersection points.
So I'll leave you with this. The next time you're playing a video game and you see this beautiful, shimmering reflection on a curved surface, just think about the complex math you now know is furiously working behind the scenes to make that incredible image possible.